We thought it might be well that we sort of get a level playing field and see if we can't get somebody to talk about the whole language of energy, the science of energy. And we have in our midst a distinguished scientist. As a matter of fact, he's a veteran of many, many years in science. And most of you have seen him and know him. He usually shows up and has a cup of coffee and a cookie so that there's minimal energy there. And in the realm of energy, and I'm sure he's going to talk about it, I remember full well that one of my professors years ago said, it's easy to understand the 3 laws of thermodynamics. The first law says you can't win. The second law says you can't even break even. And the third law says you can't even get out of the game. Well, to refine those and to talk in more detail, Turk is going to do that. I'll just simply say that he's been a distinguished professor at our university for years in chemical engineering, and he got his degree, his doctorate, before there were universities, I believe. Is that right? No, he got his doctorate from Purdue a few years ago, and it's my pleasure to introduce our friend Turk Storvick.
I have to bring my props. Professors always have a bag full of props, and so I brought some props. One of them, obviously, is a book. I brought a ball. We need that. And I need a cup. So I brought a cup. And the things I want to talk about today start with, I want to do a little bit of physics with you, and what I need to tell you about is the word work. There it rolls, see? The ball is round. Anyway, the concept of work is important, but we have to be able to define it so that if I do an experiment and you do an experiment, we get the same numbers. One of the problems we have today in our society is that people keep arguing about numbers and they refuse to do physics. And as a result, their numbers are different, and since God gave them their numbers, it's hard to argue. The second thing I want to do is to talk a little bit about how you get from thermal energy to work. In other words, I want to define work first, and then how do you get from thermal energy to work? And then the last part I want to talk about is how do I compare now, as an advocate for nuclear power, the difference between nuclear power generating electricity and coal power generating electricity. Now, I want to do a few contrasts there, and I want to leave a little time for some questions. So I'll start with the old idea of work, and I'm going to start with a book. Anybody that does physics has to have a book, right? And I'm going to use the book to demonstrate a physics experiment that has to do with work. Any object that we can hold, all right, is subject to gravitation, or the force of gravity, all right? Everybody understands that? That's an elementary concept of physics, all right? If I take this book and raise it from the tabletop to 3 feet above my head, all right? If the book weighs 2 pounds, I've done 6 foot-pounds of work. And if you do the experiment the way I did the experiment, you'll get exactly the same number, right? If, on the other hand, I have the book here and I allow it to go down and I recover the work that I put into the book, raising it, I now recover that energy, and that is positive work produced. I did work getting it up there. It'll produce work getting back, all right? That's the concept of work. It's a force times a displacement, all right? So now, one of the problems we always have when we build machinery is friction. Everybody understands what friction is? I've got a book here, and if I move my book this way, am I doing any work? According to my physics definition, no. Because I'm not changing the position of the book with respect to the source of the gravitational field. In other words, if the elevation doesn't change for this object, you haven't changed the amount of work, all right? If I set the book on the table and now push it this way, am I doing work? And the answer is yes, because it takes force to push the book, and it interacts with the table, all right? It interacts with the table, and that force times the displacement distance is, again, foot-pounds or kilogram meters or whatever the measure is. It's a form of work, all right? What happens now if I take a jug of salad oil, or let's say cooking oil, and I dump it on the table here, and then set my book on top of that salad oil, all right, besides making a mess of the book? What I really want to demonstrate now is if I now push on the book, is it easier or harder to push the book with the salad oil on the table? It's easier. It's easier. I've lubricated now, reduced the friction between the table and the book. All mechanical devices that we use every day have bearings and things in them that are lubricated to make them move with less friction and avoid. Now, where does that work energy go when I have friction? The easiest experiment I know, and where everybody has the tools to do the experiment, is this one. What happens when I rub my hands together? They get warmer. We usually do it in the winter, not in the summer, right? We usually do it in the winter, not in the summer. And if I speed it up and push harder, it gets warmer, right? All of the friction energy that we that shows up in a piece of machinery or so forth generates heat, and you have to dissipate that, and one of the ways to do that is to use lubrication. Reduces the friction, reduces the amount of heat. So you never run your automobile without lubricating oil in the crankcase, because if you do, you're going to have a problem, all right? What happens is that that engine, it won't be very long before it'll stop for you, and replacement aren't cheap. So now that's the stuff that work is all about. One of the things that we have to do, one of the things we have to do when we produce electricity usually is to generate steam. Now, why do we generate steam? Let me go back a few years. There were some Phoenicians a few years ago that discovered that if you put a pole in their boat and a piece of cloth across that sucker, if you were going downwind, you didn't have to row as hard, all right? And it wasn't too many years later, maybe only a couple centuries, maybe it's more than that, maybe 1,000 years later, the Dutch put big poles on a shaft, on a tower, and put a sail on that and let the wind turn that thing, all right? So we know that if you have a wind and a sail, or, if you will, a sail on a pole on a rotating shaft, you can produce work, right? They knew that. What's the problem with this wind machine, the Dutch wind machine? It works better in Holland than it does here because they have wind almost every day. Not so in Columbia, Missouri. We don't have very much wind here, and that's one of the reasons why we probably will never see a wind system in Columbia, except somebody says, well, I'm going to build one, but it's not going to run a sustained power output because the winds don't blow constant and long enough each day. It takes about, for the big machines that they're building nowadays, it takes about 13-mile-an-hour winds or higher on a steady basis to operate those machines and produce the electricity that they have on their nameplate, the rated power. If you don't have any wind, then the power that is produced is much less. So now, how can we fix this? It wasn't too long into this business of physics that they discovered that if you boil water in a pot, you make steam. If you put a valve in the pot and boil water, the pressure goes up, and when you open the valve, the steam comes out at a higher velocity, all right? So if I have a boiler and I make high-pressure steam, and I blow that high-pressure steam on my Dutch windmill, which I'm now going to make very differently than the Dutch windmill. I'm going to take, let's see if I've got a piece here. Yeah, I got a piece here I can do. I'm going to make it out of metal pieces that are bent like this. And I'm going to let the wind blow this way, and when the wind strikes that, it turns and goes this way. And what that does is it pushes this blade this way, all right? And so what I do is if I blow that wind on, if I put a whole bunch of these blades on a wheel, put them on a shaft and blow on them, they'll turn, and I have a turbine. That turbine can work with water, or it can work with air, or it can work with steam. Now the problem with the high pressure steam that you get in a steam boiler is it gives a much too high an energy stream. So you have to have some way of capturing the energy that strikes this blade and turns this direction. So you put another blade over here that's oriented like this that changes the direction of the steam from this way back this way, and then you put another row of these vanes over here, and it captures the energy again. You do that several times, and a steam turbine that you have at a coal-fired power plant has these vanes designed according to the aerodynamic theory that was developed to fly airplanes. So those suckers turn get the momentum that comes with that steam velocity as much as possible converted to force times displacement, which is work that you can now use to turn a shaft which will be connected to something that will produce work. And what I'm going to hook mine to is an electric power generator. All right? That's what I'm going to hook it to. All right? It doesn't make any difference what I use for fuel to produce this steam. The difference will be that if I use coal, I have a source of energy that's fairly hot, and I can make the steam, and then I can take the steam that's produced and put it through another coil through the firebox and heat it to a high temperature, well above the boiling point of the water that's in that boiler, right? And the higher the temperature and the higher the pressure, the more energy you can extract from that stream of steam as it goes through this turbine, all right? In a nuclear power plant, they use water for two purposes in the reactor. One is to extract the thermal energy, the heat, all right? And they do that by putting water in the reactor system and keeping the pressure very high so the water doesn't boil. It does not form steam, but it does form high pressure, hot water, all right? Now we need that water there for another purpose. As the nuclear reaction goes on, the neutrons that are formed during the fission of uranium, and I'll talk about that a little bit later, need to be slowed down in order to effectively produce an additional fission in another atom. And the water serves as a moderator, or if you will, a box of sand to slow these things down so that they interact with another uranium atom to cause fission and do it efficiently. So the idea is the water serves two roles. It gets the thermal energy out of the reactor, and it slows down the neutrons so they're more effective in producing additional fission to produce more energy, right? Now the hot water out of this reactor has to go through a second heat exchanger where the pressure on the outside of that heat exchanger is low enough so it does form steam. But that's going to be saturated steam, and it's going to be lower temperature, it's going to be wet, and it's much more difficult to use through a turbine because it starts to condense, it forms drops of water, and that erodes the turbine blades, gives you some problem, but we know how to solve that. And if you don't believe we know how to solve it, go over to the Callaway plant over here because they're running a turbine over there every day, and it runs for 18 months between refueling, and that's the only maintenance they do on that thing, and it really works very well. So here we are. We know we can get this, if we can get high pressure steam, run it through a turbine, we can turn a shaft, and we can produce electricity. I'm going to use the Callaway plant as an example of how this comparison between nuclear power and coal-fired power works. Understand that the nuclear power plant at Callaway produces 1,000 megawatts or 1,000,000 kilowatts as it operates at steady state. And the company that owns that, what was the name of that company? What was the name of that company? What the heck was the name of that company? They've been in the newspaper recently, and I think there's some people in St. Louis think the executives of that company are probably in charge of the weather. And some of the letters to the editor have really gotten onto those folks about ice and about wind. And I guess the funny part about this, of course, is that when the lines go down, you don't have electricity. And I don't know about you, but at our house, we've gotten very dependent on electricity. Man, when that power goes off, my furnace doesn't work, my freezer doesn't work, my lights don't work, my TV goes off. I can't even play music. And talk about being handicapped. That really does it. All right, so electricity is extremely important in modern society. We depend on that like food. And remember, this food business, you can talk about that a little bit too. I myself, when I was raising my family, was only 9 meals from a revolution. You take my food away from me and my kids for 9 meals, and I'd be one hopping mad guy, right? And I'd be out scouting. So remember that when you jerk the electricity away from these people, they can't cook, they can't do TV, they can't, wow, they're really stuck. And it's a mess. I've been there, and it's not any fun. So we need a really reliable source of electricity. The Callaway plant produces 1,000 megawatts or 1,000,000 kilowatts at steady state operation. If I were to replace the Callaway plant with a coal-fired plant, and I know this is exactly true because the same firm that runs the Callaway plant runs a coal-fired plant in St. Louis. And it is exactly the same capacity as the Callaway plant. It takes 12,000 tons of coal a day to produce that energy. 12,000 tons of coal is 1 unit train, 120 carloads of coal from Wyoming to St. Louis. And they're fussing a little bit because the trackage between those places is not in terribly good shape, and when they have derailments and the coal supply is shortchanged, or when they had a snowstorm out in Wyoming and they couldn't load and get the trains out, there got to be a little anxiety in St. Louis because if we have to shut that plant down again, the natives will probably take over because they get pretty restless when the power goes off. Anyway, so here we are. It takes 12,000 tons of coal a day to produce the same amount of electricity as you could produce in the Callaway plant. Now, I've got to talk a little bit about what the difference is. When you burn coal, I'll just talk about the way carbon goes. The carbon in the coal combines with 2 atoms of oxygen out of the air to form carbon dioxide. And that releases energy, thermal energy. That's the energy that comes out of the fire. Now, there's also some hydrogen in the coal. There's also some other stuff that oxidizes and releases heat. But we'll just focus on carbon. Now, the one thing to remember about the green part of this energy is that when you combine the carbon in coal with 2 oxygens out of the atmosphere, it forms carbon dioxide. So when I burn 12,000 tons of coal, which contains somewhere between 55 and 60% carbon, I produce approximately 28,000 tons of carbon dioxide. And that carbon dioxide is non-toxic. It's suffocating, but it's non-toxic. So what we've been doing for quite a few years is we put it out the stack. It goes in the atmosphere. And that atmospheric carbon dioxide accumulates up there because the rates at which it's sequestered or taken away from the atmosphere depends on plant growth, it depends on solubility of carbon dioxide into ocean water, a whole bunch of things that tend to be quite slow compared to the process that we use for burning this coal. Now, what's the difference? In the case of carbon combustion, you have, let's say this is the nucleus of the carbon atom. There's another one over here that's oxygen. They're about the same size, those nuclei. But it's the interaction between the electrons that are going around this nucleus that produce the thermal. What I'm going to do in the case of a nuclear reaction, I'm going to take this nucleus now, which is I'm going to call this uranium-235 isotope, which happens to be the one, when it accepts a neutron, And it does this fairly easily, but the neutron has to be moving slowly. Rather than in the design of the current reactors, we slow it down to the water. And it's really amazing that in this nucleus, I have 92 protons, which are positively charged particles, which hate each other like crazy. They don't like each other at all. But 235 less 92 gives me about 261, I think, and I don't remember the number exactly, neutrons in there, which have no charge. And the forces between those neutrons and those protons allow that stuff to be packed into this nucleus. And it's the interesting thing is that if you now take a neutron, another neutron, and put it in there, all right, what happens to this system, it starts doing this kind of stuff. It's sort of like taking a balloon full of water and giving it a big jab, and it does this kind of stuff. Except it's more profound because the amount of energy or the repulsive energy between these protons is really enormous. So when the shape changes, they push each other apart. This thing comes apart, and the protons and neutrons in each piece form the nucleus of another atom, and that's what we call fission products. At the same time, about 3 neutrons are ejected, which now pass through the water. 2 of them are dissipated. 1 of them fissions another atom. Now, the remarkable thing about this particular atom, I've got this thing, around this atom are 92 electrons. And they're flying around there. If you picture in your mind, if you can, you can believe anything if you close your eyes and try harder. So if you close your eyes and try hard now, you can see these things flying around here, and according to quantum theory, they never collide with each other. They have different orbits, and they never collide with each other. You can excite them and put them in a new orbit, but they still don't collide with each other, right? Remarkable. It's very small stuff, this. In fact, let me try to give you some idea of the smallness, right? If this is the nucleus of the uranium atom, the first electron out here circling this atom on this 1.5-inch scale of this ball is somewhere between 0.5 and 0.6 miles from this one. So the distance is enormous if you think of it in terms of the particles are extremely small, but the distances between them are very large. But I've got 92 of these electrons going around this thing, all right? Now, I'm going to take this uranium atom, and I'm going to say the following. When that thing fissions, all right, in the Callaway plant, it takes between 7 and 8 pounds of uranium per day fissioning to produce 1,000 kilowatts of electric energy. In other words, fissioning 8 pounds of uranium produces as much energy as 12,000 tons of coal, all right? Imagine that. If I take 8 pounds of uranium metal, 8 pounds of uranium metal in one piece, it'll fit in this teacup, all right? That's the quantity of metal that is fissioning to produce that amount of energy. You get enormous amounts of energy from a very small quantity of material, all right? That's the primary story. Now, how much CO2 do I form when I do this? Only if there's a fission product CO2, and there sure ain't many of those, because the nucleus normally comes apart in pieces that are approximately equal weight. There are a few smaller pieces, but most of them are it's sort of like cutting it in half. And so the atomic mass is about half of the original atomic mass of this atom, all right? That's the deal with respect to nuclear. Now, the problem we have with nuclear power is what do you do with the spent fuel? The fuel can only stay in the reactor at Callaway for 3 years. At the end of 3 years, I have to take it out because the fission products that have accumulated in that fuel interfere with the rates at which fission occurs and the power of the reactor drops off. And so we have to replace the fuel, put new fuel in. So every 18 months, we replace half the fuel in that reactor. And the radioactive fuel that comes out of there, and I understand that's very radioactive stuff. It's quote, we call it nasty, but it's nasty stuff, and they store it in a pool next to the reactor. And it turns out that pool is about twice the size of the Olympic pool we have over in the rec center over here. It's a little deeper, and they put a little boron salt in that water, and that slows down neutrons, and it makes that water in that reactor serves as radiation shield, all right? And that's the stuff that we have to reprocess. And that's the thing I spent about 10 years on at the plant down here. The Japanese said we need to understand a little bit about separating spent nuclear fuel, and they said, we'll fund the project if you'll do the work. I said, I'll do the work, and I know that you can do the separation. And what we need to do, of course, is a commitment. We need a commitment. And it turns out that the federal government now is putting lots of money, or will be putting lots of money into this project. The people at Ameren now are currently drilling holes over at Callaway, and they're looking for solid foundation for a new plant that's going to be installed over there, and I think that plant will probably be operating about 2012 if everything goes according to plan. Now, I'll take questions. Yes?
Keep going with your last point. What can you do with spent fuel?
What can I do with spent fuel? Yeah, what I do with the spent fuel is I separate out the uranium. Plutonium is formed during this process in the Callaway plant. 40% of the energy that's released in that plant during the 3 years that fuel is in the plant, in the reactor. About 40% of the energy that's released is from plutonium that fissions, just like uranium-235. And the plutonium is produced when the major fraction of the uranium, which is the U-238 isotope, accepts a neutron, becomes uranium-239, which after a couple short half-life decays becomes plutonium-239, which is a good reactor fuel. Yes?
Yeah, there's always a downside. And obviously, you mentioned the downside with radioactive waste, and I take it that your answer is reprocessing.
Yes.
There must be a downside to processing, at least at this point.
Excuse me, the last word.
Is there a downside to reprocessing at this point?
Well, yeah, there is. There's always a downside to everything. There's different ways to proceed with the reprocessing. The process I worked on is what we call a dry process, where we worked with electrochemistry, and we converted all the metals that were in the spent fuel, or the simulated spent fuel, to metal chlorides, and then we electrochemically deposited the metals out of that chloride solution, or we used oxidation reduction potentials and reduced the metal out of the salt into a liquid metal alloy from which we could do the electrochemical separations. And we demonstrated that that can be done at a 1/2000 commercial scale. It does work. How much time have I got?